Welcome to another episode of the Mindgasms podcast. We're going to do another delusional episode today. This is part 10 of Delusional on Deleuze's thoughts on Bernhard Riemann, who is a 19th century German mathematician, and this is based on another one of those essays from the book called Deleuze's Philosophical Lineage. And we've got Chief Keefe here again, of course, for that. So would you like to start off with an introduction, as you always do, Tim, to Bernhard Riemann?
Sure thing. His name is actually pronounced Riemann.
Riemann. Oh, okay.
Riemann. Yeah, the
Riemann.
IE is E, EI is I. That's in German.
Oh, okay. It's a little different from my German last name, which is pronounced Meitzer.
Yes,
Yeah.
Meitzer. Okay, so I was a little on the fence to look at this essay because of the fact that Riemann is probably one of the most famous of the mathematicians of the 19th century, and I was afraid that it was going to be a little bit too much on the mathematical side. I understand the importance and I appreciate the importance of mathematical philosophy, but I tend to stay away from it because sometimes it can be over my head. But as I was reading through it this morning, I thought, yeah, we could do this because it's not so heavy on the math. There's some important ideas that Deleuze and Guattari had taken out of this, and why the hell not? So we'll go ahead and save Sigmund Freud for next time because there's an awful lot in there to unpack. And I decided to go with this one instead of the previous essay to this one, number 9 in the Philosophical Lineage book, which is on Juan Wronski and Francis Warren. I didn't think that was that important, so I decided to skip and go to Riemann. We might go back and look at Wronski, but at this point I'm unsure.
Now, who is Wronski? I've never heard of him before.
So Wronski was a Polish mathematician, philosopher who was, I'd never heard of him either. He's one of those obscure figures, kind of like Solomon Maimon, except Maimon is a little bit more well-known, particularly in Jewish circles. But he was heavily influenced by Friedrich Schelling, and his main philosophy was on messianism. So, again, I didn't think it was too important to cover, and Riemann is definitely important.
Okay.
So, I made an executive decision.
Okay.
So let's go ahead and dive in. Riemann. So those that are not really familiar with mathematics would not know who Riemann was, but math geeks certainly should know his name because what Einstein was to Newton, Riemann was to Euclid in the field of geometry. Now, Riemann had done other work, things with number theory and stuff like that, but he's mostly well known for his developments as a discovery in geometry, which set Euclidean geometry on its head, and also paved the way for Einstein later on.
So it's also perhaps similar to how Marx turned Hegel's idealism on its head?
No, not to the same extent.
No? Okay.
No. The Riemann, I'd say, is more important than Marx is, particularly in mathematics.
Okay.
So let's dive right in. I'll skip a little bit of Riemann's background. He was a student at the University of Göttingen, which is near the center of Germany, and he lived a relatively short life. He died when he was 39. He definitely made an impact. So I'm using the one website, Science News, which is this is an article that was published last year. Gives a nice summary, a non-mathematical summary of what Riemann's important contributions were. So I'll go ahead and read this. So one lecture in 1854 on the hypothesis which lie at the foundations of geometry. Riemann cut to the core of Euclidean geometry, pointing out that its foundation consisted of presuppositions about points, lines, and space that lacked any logical basis. As those presuppositions are based on experience and, quote, within the limits of observation, the probability of their correctness seems high, But it is necessary, Riemann asserted, to, quote, inquire about the justice of their extension beyond the limits of observation, on the side both of the infinitely great and of the infinitely small. Investigating the nature of the world, he said, should not be hindered by too narrow views, and progress should not be obstructed by traditional prejudices. Okay. So basically what the article is saying here is that Euclidean geometry, Euclid was the ancient Greek mathematician from many centuries ago. And up until Riemann's time, Euclidean geometry was the only form of geometry that was really accepted widespread. And
Oh, okay.
Euclidean geometry is what you study in high school.
Right.
So those of you that remember Euclidean geometry is what's the definition of a point, what's the definition of a line, triangles, circles, rhomboids, axioms and proofs that you have to do, things like that. All this is the update of Euclidean geometry. You don't have to go back and read the what's it called? The Elements, I think, which was the actual treatise in which Euclid had laid out the principles of Euclidean geometry. So, what Riemann was.
I remember tutoring a few of my students last year in what sounds like Euclidean geometry.
Yeah, you normally study Euclidean geometry. I don't think high school students even touch Riemannian geometry. Yeah. It's a little too advanced for them, I think. But anyways, okay. So what Riemann was saying in this article on the hypothesis was light the foundation geometry. So whatever one says about points, lines, and space in Euclidean geometry, they're presuppositions. These are not taken as self-evident. This may seem to be the case in our observations, but what about things in space in particular that do not fit neatly into Euclidean geometry, Euclidean lines? Nobody seemed to talk about that up until this time. So he was questioning the presuppositions about points, lines, and space because there was a logical basis beneath them. I mean, one definite thing you take away from Euclidean geometry is that the shortest distance between 2 points is a straight line. Okay. That's not necessarily the case in every case, as we will see shortly.
Mm-hmm.
Sorry, my throat is dry. So continuing, freed from Euclid's preconditions, Riemann derived an entirely different non-Euclidean geometry. It was this geometry that provided the foundation for general relativity, Einstein's theory of gravity, 6 decades later. Continuing, Riemann's insights stem from his belief that in math, it was important to grasp the ideas behind the calculations, not merely accept the rules and follow standard procedures. Euclidean geometry seemed sensible at distant scales commonly experienced, but could differ under conditions not yet investigated, which is just what Einstein eventually showed. Okay, so Riemannian geometry enabled Einstein, the theory of relativity, because if it did not, then Einstein probably would not have been able to get the general relativity theory off the ground. Would have been stuck in Newtonian mechanics.
So he's really important then, for sure, like you said.
Oh, yes. Yeah. Yes, he is that important. Okay. So continuing, Riemann's geometrical conceptions extended to the possible existence of dimensions of space beyond the 3 commonly noticed. By developing the math describing such multi-dimensional spaces, Riemann provided an essential tool for physicists exploring the possibility of extra dimensions today. Okay? So there are more than 3 dimensions.
Right.
4th, 5th, 6th, 7th, and whatever. Or there are dimensions that exist at the same time, multidimensional.
Yeah.
That's it for a summary.
Okay.
Okay, so let's dive into the essay in the Lineage book. This is essay number 10, page 190, by Arkady Plotnitsky. Okay. So I'll go ahead and skip the first paragraph in which Plotnitsky says that mathematics played a major role in Deleuze's thought, beginning with his engagement with calculus and Leibniz. We'd seen this before in the Leibniz essay. And Leibniz was a major philosophical influence on Deleuze. But Riemann is probably the most important mathematical influence on Deleuze, especially in the later works, particularly with space and in his collaborations with Félix Guattari, who we saw last time with the essay on Marx. Okay. So we did a quick summary from that article. Going to the next page, number 161, Plotnitsky says, from this perspective and his concerns, his significance for Deleuze's philosophy, Riemann's greatest contributions are, first, his concept of spatiality, and secondly, his capacity of combining different fields in approaching problems apparently belonging to a single field. What I call non-Euclideanism, mathematical or philosophical, is conceived on the model of Riemann's thought and practice as defined by these two phenomena. Okay. So for Riemann, it's about space, what he had to say about space and spatiality. And then he used different fields such as geometry, algebra, analysis, and topology to come up with the non-Euclidean space.
What's topology?
Topology is the study of surfaces, that's topography. Topology is about spaces, places in space. Okay.
Okay.
So a point here, a point there, a line drawn between the two, a point here, a point there, a line between the two, and drawn between the other two spaces. That's topology.
Is it a mathematical discipline?
Yeah, it is a mathematical discipline.
Okay.
So rather than give a simplistic explanation, let's see what Wikipedia has to say. Okay. Concerned with the properties of a geometric object that are preserved under continuous deformations, such as stretching, twisting, crumpling, and bending, but not tearing or gluing. Okay.
Okay.
For example, do you know what a Mobius strip is?
No.
Okay, you've probably seen one. I won't give the picture here, but if you take a strip of paper, when you twist it, and then you attach both ends together, you have a Mobius strip. Because wherever you start on the one side, as you're going through, you're going to remain on that side even though you're twisting through the shape.
Oh, okay.
That's what a Mobius strip is.
Okay.
So a Mobius strip is one example of something you study in topology. Something else might be you're taking a sphere and you squash it, maybe like a basketball that's out of air.
Mm-hmm.
Stretching, twisting, crumpling. So this is what topology studies. Why?
Oh, that's
Because
interesting.
this is not something that you can easily do with Euclidean geometry.
Yeah.
You don't have a perfect sphere. You don't have a perfect circle. So you need something that would allow you to measure the distance of 2 points on that space,
Right.
on that particular shape.
Right. Yeah, that's interesting.
Yes. Okay. So next page, page 192. All right. One concept from Riemann was what he called the manifold, which, again, let's go to Wikipedia. So in mathematics, a manifold is a topological space. We already defined what topology is. That locally resembles a Euclidean space near each point. More precisely, each point of an n-dimensional manifold, n meaning however many dimensions you care to cite, has a neighborhood that is homeomorphic, meaning of the same shape, to the Euclidean space of dimension n. In this more precise terminology, a manifold is referred to as an n-manifold. Okay, so another way that you can describe a manifold is that it is as it says, a topological space that locally resembles Euclidean space. So of the whole, it's not a Euclidean. But near each point, you have a Euclidean space, say a circle or a square or a rectangle or something like that. That's what a manifold is in a mathematical sense.
Okay.
Okay, so Riemann defined geometry as manifolds. Spatiality actually is manifolds. And Plotnitsky says, Riemann's concept of spatiality as manifoldness allows one to define certain spaces as patchwork-like assemblages of local spaces, without in general the overall space possessing the same type of structure as those local subspaces do, while the latter, meaning the subspace, may differ from each other as well. Okay? Patchwork-like assemblages of local spaces.
Okay.
Okay.
This is interesting, just like trying to think about this visually.
Yeah, it is.
Yeah.
So how can we best explain it? Okay, so Instead of looking at a basketball, okay, basketball would be more or less a perfect sphere, which you could study with Euclidean geometry. You let the air out and you squish it together, all bets are off. Now you have to resort to something like topology to study what that is. So this is one object that exists within a space, and it's a local space. So spatiality is a manifold, a collection, assemblage of local spaces without the overall space. Okay, so you could have, say, a cube. That's a local space, but many different spaces within it. Say, a line or a square, a two-dimensional object, a sphere, the squashed basketball, or something like that. So within this one space, there are many different spaces, and this is the manifold.
Okay.
Okay?
That's so interesting.
Yeah. So
It's
continuing.
Yeah.
These qualities give a Riemannian space heterogeneity, which is, however, interconnected by virtue of the overlapping between local spaces. In particular, these local spaces can be considered as infinitesimally Euclidean, while the overall space is, in general, not a Euclidean space. The overall space may be given a global determination. In particular, it may be given an overall metrical structure, determined by the formula for measuring the distance between points that varies locally, and that infinitesimally, that is when the 2 points in question are close to each other, converts itself into the formula for measuring distances in the Euclidean space. In particular, what Riemannian space is good for is something like curvature, which you can't easily do with Euclidean space.
Okay.
Euclidean space doesn't study curves.
So I'm a little confused about one of these aspects relating to what you just said and connecting it to what you said earlier about is one of the points supposed to be that if we're looking at a particular space, it's made up of manifolds, and part of that meaning is that if you can identify a particular point in space and it's made up of those manifolds, but that particular location is not necessarily it's not necessarily defined within space as a general thing, like all of existence or something like that, or am I way overanalyzing it or missing something here?
I think you're way overanalyzing it. So once
Okay.
again, Riemann defines spatiality as the manifold.
Okay.
Okay. So the manifold is, you can use a manifold to define, as Leninsky says, defining certain spaces as patchwork-like assemblages of local spaces, without in general the overall space possessing the same type of structure as these local subspaces do. Okay. So the point here is kind of like, I don't know if you've worked with Photoshop before or any kind of image processing application.
Probably a little bit.
Okay. So if you work with something like that, you probably remember that when you're putting together an image, it's actually a composite. It works with something called layers. So if you're taking a piece of paper and you're sketching out something on it, okay, say, your face. You could sketch out something in your face. Okay. Then you take crayons or colored pencils or something like that, and then you start filling in the spaces where your eyes are, where your eyebrows are, where your lips are, and so on. You've already defined these spaces while on the same plane, the same piece of paper. And you're doing this in 2 dimensions. Now, when you're using an imaging program, coloring that in, whatever the space is, creates another layer on top of the already existing layer. So you've drawn your face on the one layer. If you color an eyebrow, that's another layer. If you color a second eyebrow, that's another layer. If you color your lips, that's another layer. See where this is going? So the image is a composite. This, I think, is something close enough to what Riemann was defining as a manifold. Okay. Not everything exists in one space, or rather it does, but the space itself, the Riemannian space, again, this is the difference between a Riemannian and Euclidean space. So Euclidean infinitesimal, so you could have spaces or shapes or whatever it is close enough infinitesimally to Euclidean that exists in a non-Euclidean space. This is the Riemannian space, the manifold.
Okay.
Okay. This is a little difficult to grasp, understand. We're not going to get too much into the nitty-gritty about what the math is. Just understand about this manifold, because Deleuze is going to. This is an important concept for Deleuze.
So, like, in the sense that a Euclidean shape could exist in a non-Euclidean space, like in the like within a non-Euclidean space, you could still have a supposedly perfect sphere like a basketball or something like that.
Well, you could, but it wouldn't be a Euclidean sphere.
Okay.
Okay. So later on, Plotninsky makes this mention, is that if you take the basketball, the more or less perfect sphere, you put a point on the one end, you put a point on the other end. Okay. Now Euclidean space is the shortest distance between two lines is a straight line. But that's hard to do on the surface because you have a curvature. Okay. You can't do this in Euclidean space. You would kind of have to draw it. You take your pen and then you draw it from one end to the other, and then you would try to take a ruler and measure that. It's hard to do unless you maybe have a tape measure, but then you're not going to get the exact measurement. However, if you take that basketball, let the air out, and then you squish it together, both points now have come as close as possible to each other.
Mm-hmm.
But that's not a straight line.
Right.
Necessarily. Or you could let the air out and then warp it, the basketball, somewhat. And then the two you could take, let's see, what's the best way to do this? You squish it until it's like until it looks like a sandwich or something. Then bend it to where the points are facing each other, and you can measure that distance. But you're not measuring it on the shape. Okay. It's a little difficult to explain this. I would say it'd be better to show it. But the whole thing about Riemannian geometry is that you can measure the points. You can measure 2 points on a sphere or a cube or something like that, whatever it is, in such a way where you don't have to use Euclidean geometry, because you wouldn't be able to do it.
Oh, okay.
Okay. Not to mention the fact that with this concept of spatiality, as we saw in that previous article, is that this allows for multiple dimensions.
Right.
You're not trapped in three-dimensional space.
Yeah. Yeah. That's why it's so interesting to think about that.
Yeah.
Like, because we're used to thinking in 3 dimensions.
Sure, and that's what Riemann was getting at, is that
Yeah.
Euclidean geometry is based on presuppositions, much of which came from what our perceptions are. Well, yeah, if I got a point here, I got a point here, and if I use a straight ruler, this is the shortest distance that I could come up with. I'm not going to try to do a roundabout way to measure it. It's not going to help at all. It doesn't give me what I'm looking for. So these were kind of based on prejudices, which were limited by our senses and so on and so forth. However, the thing about mathematics is, particularly when you're going from the 19th century on, is that it gets a lot more complex. And this complexity allows somebody, particularly with the calculus, to measure curves or curvature. Think of space exploration. You wouldn't have space exploration or, using telescopes in low Earth orbit or something past that, because space in the universe doesn't exist within a Euclidean space, or it doesn't operate under Euclidean principles.
Right. So is something like measuring the circumference of something round like a basketball part of non-Euclidean geometry, or is that still part of Euclidean geometry?
Well, it depends on how you measure it. Okay.
Okay.
You can measure the circumference using the principles of Euclidean geometry. I mean, if you remember something about geometry, yes, this is how you measure the circumference. You're given certain values for whatever the formula is to measure the circumference. But again, this exists in more or less two-dimensional space, and the assumption is whatever you're measuring as a perfect sphere, circle, or something like that. But real life is not like that. When you take the basketball, is it really a perfect sphere? Or something else is that the planet Earth, is it really a perfect sphere? No, it's not. It's got
No,
bulges here and there.
it's a I forget what Hunter Motz said that it's called. It's like a
Colloid?
colloid spherical object or something like that. I don't remember.
Yeah. So it's not a perfect sphere.
Yeah,
And not to mention, you can't measure the Earth just by your observation. You can't take this gigantic tape measure of thousands and thousands of miles to try to measure it. So you have to come up with other ways to do so.
yeah, yeah.
Okay.
That's what I was thinking about when we were first starting this. That like when you talk about a circle or a square or something, there you can rarely find things that are perfect squares or perfect circles, at least that are made naturally. Like humans make things that are like that.
Sure. You could, I mean, you could easily take a compass on a piece of paper and sketch out a perfect square.
Yeah,
90-degree angles, your sides are of a certain definition. However, the problem is, and we'll see this later in the Plotnitsky essay, you are also dependent upon however that measurement tool is calibrated.
yeah,
I mean, when you're looking at a ruler, when you're looking at a compass or something like that, that's already been defined. But what happens when that doesn't apply?
you
How
need
are
a
you going to
new
measure it?
you need a new method of measurement.
Bingo. So I don't want to spend too much time on this. Let's continue. Still on the same page, page 192. Plotnitsky says, okay, so for the first component, Riemann had defined spatiality in terms of the manifold. The second main component of non-Euclideanism is defined by the theoretical practice, mathematical or philosophical, of combining different fields and approaching objects defined or problems formulated within, and apparently belonging to a single field. Riemann's concept of a manifold was developed by bringing together algebra, analysis, and geometry, and thus by means of a multiple or manifold, heterogeneous yet interactive, theoretical practice that he deployed and expanded throughout his work. So in other words, he didn't limit himself to one particular area.
Yeah, it's good. I like it when intellectuals are more interdisciplinary in the way that they do things.
Yes, but this was also within mathematics itself, because stop and think about it. You have some mathematicians that are specializing in maybe number theory, others that are in geometry, others that are in algebraic theory, higher order algebra or something like that. A friend of mine used to really get off on what was he looking at? I think it was statistics and number theory. Some of which was over my head. But you take all that together and you can come up with some pretty cool things, interesting things. Hence what Riemann did.
Yeah,
Okay. So next page, 193. Plotnitsky continues. Riemann's concept of the manifold allowed him to encompass both Euclidean and non-Euclidean geometry within a single, more general concept, which also enabled it to serve as the mathematical basis for Einstein's non-Newtonian theory of gravity, known as general relativity. So Riemann never did away with Euclidean geometry completely. He just said it was limited, and that it was based on presuppositions which were never questioned.
right.
Okay? So, and then we've already seen this before, is that this also paved the way for Einstein. Now going to the bottom of the page. Okay, now we're coming into Deleuze and Guattari. So Riemann is particularly important for the both of them when they're writing Capitalism and Schizophrenia. Okay, so Plotnitsky continues. A philosophical concept is not an entity established by a generalization from particulars or any general or abstract idea. This is what Deleuze and Guattari had to say about concepts in What is Philosophy, one of their last collaborative efforts, which came
Which we
out.
talked about before.
We talked about that before, right? So, again, a philosophical concept is not an entity established by a generalization from particulars or any general or abstract idea, but a multi-layered conglomerate entity. Quote, there are no simple concepts. Every concept has components and is defined by them. It therefore has a combination. It is a multiplicity, could one even say a manifoldness? There is
Uh,
no concept with only one component. Each concept is a multi-component conglomeration of concepts in their conventional senses, figures, metaphors, and so forth, which form a unity or have, as Deleuze's own concepts often do, a more heterogeneous, if interactive, architecture that is not unifiable. The architecture of Deleuze and Guattari's concept of the concept is itself defined in part by Riemannian spatiality as manifoldness, by linking the very invention of philosophical concepts to a spatial and, in part, Riemannian concept, the plane of immanence. We've seen this before.
oh, cool.
Thus making the space of functioning of a given concept of Riemannian space. Okay, so in other words, the thing about the concept is, as they both said, it's not a simple thing. If we have the concept of justice, for example, okay, so justice is a notoriously difficult concept to define. You can define it by using other concepts. You can't point to it and say, this is justice. It's not a physical thing, not a corporeal thing. You can point to justice as an action and say that what they are performing is an act of justice, or what they have done. Justice has been served. But also, what does justice mean? Fairness, avoiding putting somebody in prison. What are the foundations of justice as defined? How is it defined here in the 21st century as opposed to in the 18th century?
Mm-hmm.
So this is where they take in
Yeah.
the Riemannian notion of a manifold and applying it to concepts.
Yeah. Yeah. Foucault wrote a great book about that in Discipline and Punish in terms of the concept of justice around that same time period too.
Yes, not to mention the concept of the prison.
Yeah, exactly.
Okay. So we've mentioned the plane of immanence. Let's go ahead and redefine that. We've already looked at it once before. So you can, using the Wikipedia as a means, the plane of immanence is a founding concept in the metaphysics or ontology of Deleuze. Immanence, meaning existing or remaining within, generally offers a relative opposition to transcendence, that which is beyond or outside. Deleuze rejects the idea that life and creation are opposed to death and non-creation. He instead conceives of a plane of immanence that already includes life and death. So in other words, life and death are not separate. They already exist together within the same plane.
Right.
Deleuze refuses to see deviations, redundancies, destructions, cruelties, or contingency as accidents that befall or lie outside life. Life and death were aspects of desire on the plane of immanence. This plane is a pure immanence, an unqualified immersion or embeddedness. An immanence which denies transcendence is a real distinction, Cartesian or otherwise. Pure immanence is thus often referred to as a pure plane, an infinite field or a smooth space without substantial or constitutive division.
Yeah, I like that. I
Okay,
always
that's
like the plane of immanence. It's really an interesting concept, and I can see how what the author is explaining in this essay about how it relates back to, as you were saying, Riemann's concept of the manifold.
right. Because again, with the space is that if you were taking it from Euclidean, is that Euclidean is separate. Here's a circle, here's a square, here's a rectangle, here's a straight line, here's a right angle triangle. These denote separate things. But the manifold is what includes all of that.
Yeah.
It's I mean, because when you stop and think about it, it's when you're thinking about everyday life and the things that are in everyday life, it's an assemblage of many different things. I'm
Yeah.
sitting here at my desk and I have my iPad, I have my keyboard, I have my mouse, I have a cup of water, I'm looking at my screen, and so on and so forth. This is just an assemblage of many different things that make up my desk.
Hmm.
Okay. So that configuration, explained in a certain sense, is the manifold, different shapes that exist within that.
Right.
And Deleuze and Guattari took that and applied it to concepts. So a concept, for example, of justice, truth even, truth is a concept. Many different things go into the concept of truth. You're not pointing to just one thing. Truth is not simply correspondence to something that exists in reality.
Yeah, as we talked about with the correspondence theory of truth the last time we talked with Hayden.
Yes, exactly. Okay, so Platinsky continues. He said, thinking proceeding by deriving propositions from axioms according to proscribed rules in the manner of Euclid's elements, rather than by posing problems. Okay.
Your audio got cut off for about 10 or 20 seconds there.
Okay, I'll read that again. From difference in repetition to what is philosophy, philosophical thinking is seen on a mathematical model as problematic, thinking defined by posing problems, rather than theorematic, thinking proceeding by deriving propositions from axioms according to proscribed rules in the manner of Euclid's elements, rather than by posing problems. Okay, so philosophical thinking does not proceed by theorems. It proceeds by asking questions.
Makes more sense.
Makes more sense. Now, this is how Deleuze and Guattari approach it. There are many different ways of approaching, well, what is philosophy? What is philosophical thinking? Well, philosophical thinking is getting down to the simplest elements that one can. This was Wittgenstein's project in the Tractatus. Simplest simplest atomic sentences that describe the world and its correspondence. We're getting down to the nitty-gritty. This is a foundation from which we can proceed to ask other questions. Okay, that's theorematic.
Right.
Okay, moving on. Planinsky says, thus, a philosophical concept corresponding to a mathematical or a scientific object could also be discovered by mathematics and science, now working as philosophy in Deleuze and Guattari's definition. Thus, as they contend, quote, when an object, a geometrical space, for example, is scientifically constructed by functions, its philosophical concept, which is by no means given in the function, must still be discovered. On the other hand, it is a complex question where and how, and in what order of invention, among mathematics, physics, and philosophy, a given philosophical concept of space, say Euclidean or Riemannian, has emerged. In particular, Riemann may be seen as primarily responsible not only for many key mathematical, geometrical, and topological features of his concept of space as manifold, but also for many of its key philosophical aspects, even though both Leibniz before him and Einstein after him contributed significantly on both scores. So what Riemann was getting at with geometry was to determine what the concepts were behind the mathematics, and not just take them as a given.
Right.
Which is what Euclidean geometry was, as he contended. They were based on presuppositions. We take these as evident.
That seems to be like almost the way that science works in general. Like you have a theory, and then later on someone realizes, hey, they didn't question those assumptions, and then they form a new theory, and then it keeps continuing.
Right. So that's how science should progress. And in fact, one could argue is that that's how it progresses, has been progressing for many, many years. But what about the scientific method itself?
Yeah, that's for sure. Yeah.
Okay, so philosophers of science have had a field day with that. What counts as science? If you're looking at somebody like Bruno Latour with actor network theory, in that the scientist also creates in terms of not just discovers.
Yeah. Yeah.
Yeah.
It depends on how you define it.
Right. So in What is Philosophy, Deleuze and Guattari, among many other things, problematic asking questions, which is in the creations of concepts. Okay, concepts are not fixed. One concept has a lot in it, using the Riemann notion of the manifold. And then that concept can, in turn, change. In fact, it does change over time. It could be tossed out in favor of something else because it's no longer useful.
Yeah, for sure.
And that new concept could take some of the other components, some of the same components from the previous concept to utilize it. If we're talking, let's go back to Newtonian and Einstein. So because of Einstein, the Newtonian mechanics never went away completely. It's still around. But the theory of relativity broke out of its confines.
Mm-hmm.
It never completely supplanted Newtonian mechanics.
Yeah.
Yeah.
Yeah. You still
Okay.
need to use it for like even for space travel, like you mentioned before, right?
Yep. For sure. For sure. All right. So same page, page 195 at the bottom. Philosophy and Mathematics and Deleuze-ional. So Plotninsky continues. In What is Philosophy, Deleuze and Guattari define thought in terms of its confrontation with chaos, a great enemy and a great friend of thought, and its indispensable ally in its yet greater struggle against opinion, doxa. So doxa is a chief Greek philosophical term. We saw this with Plato. Doxa is mere opinion. It is in opposition to episteme, which is knowledge, particularly knowledge of the forms.
Okay.
Okay? Mathematics or science, philosophy and art are particular forms of thought in this confrontation. Chaos itself is given a particular concept as well. So, quoting from What is Philosophy, Deleuze says, chaos is defined not so much by its disorder as by the infinite speed with which every form taking shape in it vanishes. It is a void that is not a nothingness, but a virtual, containing all possible particles and drawing out all possible forms, which spring up only to disappear immediately, without consistency or reference, without consequence.
Wow, that's an interesting description.
So let me read the first sentence again. Chaos is defined not so much by its disorder as by the infinite speed with which every form taking shape in it vanishes.
So everything is quickly vanishing within the void.
In chaos. So stop and think about this for a minute. In order, things are kind of stationary.
Mm-hmm.
They might be changing, but they're changing very slowly that nobody notices.
Yeah.
Chaos is the opposite. So the common definition of chaos is that there is disorder, but the disorder is that the objects, the things within one's view, one's space, are quickly either breaking down, speeding up out of the way, disintegrating, or things like that. Chaos emerges
Right.
where there was order before. So Deleuze again is pointing out that chaos is not just about disorder, it's about the infinite speed, because it could speed up infinitely, with which every form is taking shape and it vanishes. When there is order, the things come in to being and they stay for a bit. So their change is very, 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 very slow.
That's a
Okay.
very evocative way to describe chaos. I like it a lot.
Yeah, I like it too. Okay. So continuing, Plotninsky says, the difference between philosophical and scientific, including mathematical thinking, as confrontation with chaos, is defined by their determination in terms of, respectively, concepts and functions. Mathematically, functions rigorously relate numbers or other entities to each other according to specified rules. Okay, let me read that again. Mathematically, functions rigorously relate numbers or other entities to each other according to specified rules. According to Deleuze and Guattari, this is another quote from What is Philosophy, they say, quote, the object of science is not concepts, but rather functions that are presented as propositions in discursive systems. Let me read that again. The object of science is not concepts, but rather functions that are presented as propositions in discursive systems. So a proposition, we've covered this before, is something that retains a truth value. Is it true or false? Discursive systems, discussion, questioning, supporting, not supporting, disproving, proving, disproving, and so on. That's a discursive system. So to take a concept like gravity, okay, gravity is not a concept. Gravity is rather functions that are presented as propositions in discursive systems. So the discursive system, what do we define gravity as? And we make propositions that gravity always fill in the blank. Gravity never fill in the blank. Gravity is fill in the blank. Okay, these are all propositions within the systems. Okay, makes sense so far?
Yeah.
Okay. They continue. The elements of functions are called functives. A scientific notion is defined not by concepts, but by functions or propositions. This is a very complex idea with many aspects, as can be seen already from the use to which it is put by mathematics and biology, respectively. Nevertheless, it is this idea of the function that enables the sciences to reflect and communicate. Science does not need philosophy for these tasks. On the other hand, when an object, a geometrical space for example, is scientifically constructed by functions, its philosophical concept, which is by no means given in the function, must still be discovered. Furthermore, a concept may take as its components the functives of any possible function without thereby having the least scientific value, but with the aim marking the differences in kind between concepts and functions.
Okay, I didn't quite get that part there about uh, a function able to have particular functives without being tied to a particular concept, or I think I'm misquoting it a little bit there, but that section there.
Okay, let's go back to the earlier one. The elements of a function, and a function is defined as that which relates numbers or other entities to each other according to specified rules. Okay, it's the relationship, strictly defined. A function is made up of functives. Okay. So then they say a scientific notion is defined not by concepts, but by functions, relations, or propositions, something that retains a truth value. So then, again, they're saying when an object, a geometrical space, for example, is scientifically constructed by functions. Okay, so a geometric space is not something well defined. It's constructed like a square. Okay, that's something in the geometrical space. Scientifically constructed by functions. A square is made up of straight lines, of angles, points on the line. Okay, these are all the construction there. It's not, there it is. It's just self-contained. When it's scientifically constructed by functions, its philosophical concept, which is by no means given in the function, must still be discovered. So what is the concept behind the square? If it's not self-evident, it's not given in the function, you still have to discover what it is.
I guess the concept would be that it's a particular kind of shape.
It's a particular kind of shape, but what defines the shape? Other shapes.
Is it what would be called the functives? Like like you, as you described, like straight lines or something like that in terms of a square, or
Could be.
okay.
Could be. Okay. So then continuing, a concept may take as its components the functives of any possible function without thereby having the least scientific value, but with the aim marking the differences in kind between concepts and functions.
Yeah, that part right there before the last part you just said, without having the least scientific value. You there? You there, Tim?
Sorry, I had mute.
Oh, okay.
Yeah, so as I said with a concept, it's a manifold comprised of many different things. And so with any possible function, you can take the functives, combine them together to create the concept, and you don't have to rely on science to find out what it is.
Okay.
And the least scientific value, because a concept is underlying whatever the science is. But can science really prove, or can it really investigate what its concept is?
No, not using the scientific method, really.
Right. Because if we're talking about the concept of gravity, okay, that's taken as a scientific concept. But what does science have to say about gravity itself? Can you prove that gravity exists?
No.
Yes and no. We'll see
You can
this later.
prove, I guess, like, you could say, you could arguably prove that gravity exists because you can, like, you can, I don't know, like in space travel, for example, you can factor in calculations about the way you think that gravity works, and it works correctly. Therefore, gravity exists because those calculations match what you need to do involving gravity, or something like that.
Right. And you can rely on calculations and the instruments that provide the calculations to show that gravity exists and that it's
Yeah,
here. But it's not something that you can point to. Gravity, as we know from science, is a force. But you can't say there's gravity.
yeah,
That's something that exists in space. Rather, gravity is kind of is a concept that exists through relations, and that you're taking, again, as they define it, as functives, so the functions. And this provides the grounding of the concept, the scientific concept of gravity, which then science takes as a given and then proceeds forward.
yeah,
Okay? So within the
yeah,
same quote, they continue. They say philosophy wants to know how to retain the infinite speed while gaining consistency by giving the virtual a consistency specific to it. Okay, we've seen this before with Deleuze and the virtual as opposed to the actual. So you could say that gravity, in some respects, is a virtual concept, not an actual concept.
yeah,
Okay, just like there are a lot of other scientific concepts you could say are virtual.
yeah, yeah,
Okay,
for sure.
continuing. The philosophical sieve, the sieve is, that metal thing that has lots of little holes that you strain pasta through, as a plane of immanence that cuts through chaos, selects infinite movements of thought, and is filled with concepts formed like consistent particles going as fast as thought. Science approaches chaos in a completely different, almost opposite way. It relinquishes the infinite speed in order to gain a reference able to actualize the virtual. Let me read that again. Science approaches chaos in a completely different, almost opposite way. It relinquishes the infinite speed in order to gain a reference able to actualize the virtual. Okay, then continuing. By retaining the infinite, philosophy gives consistency to the virtual through concepts. By relinquishing the infinite, science gives a reference to the virtual, which actualizes it through functions. Philosophy proceeds with a plane of immanence and consistency, science with a plane of reference. In the case of science, it is like a freeze frame. It is a fantastic slowing down.
Hmm.
Okay.
It's making it sound like like a plane of immanence is more reflective of reality than the scientific worldview in a way.
Yes, that's one good way to look at it, because what science is trying to do is trying to fix things, as
Yeah,
in fixing a point. Okay. So with their definition of chaos, things are speeding up and speeding up and speeding up, so that way stability breaks down.
yeah,
That's chaos. And chaos is, by one definition, producing disorder. Okay. Science doesn't like to deal with disorder. It likes to deal with things in an orderly fashion. So instead of the plane of immanence, which is the way Deleuze and Guattari define it, is that things are speeding up infinitely.
Yeah.
Science is taking that, changing it to a plane of reference and slowing things down and fixing them in place so it can manipulate them, make its study, come up with its functions, with its, having the theorems, proving the theorems, and so on and so forth. So it's slowing things down and fixing them,
Yeah.
like a freeze frame, he says.
Yeah. Yeah. It's
Okay.
interesting.
So there is a distinct difference between philosophy and science.
Yeah.
Now, also in What is Philosophy, they talk about art, but we don't cover art here. Art is another realm of experience and way of describing things.
Yeah, for sure.
Okay, so the next page, page 197. Plotnitzky says, philosophy's thought thus tries to hold to a concept that traverses a plane of immanence with the infinite speed of thought and to give this plane consistency. The plane of immanence is itself a complex multi-component philosophical concept. I'll read that again. The plane of immanence is itself a complex multi-component philosophical concept.
So the plane of
The main
immanence
point,
is a manifold.
yes, the main point here is that, in contrast to philosophy, science freezes chaos and slow motion or freeze frames. Sometimes, especially in physics, literally photographs the physical processes considered. For example, if you're looking at subatomic particles are whizzing around at an almost infinite rate of speed. You can't perceive them with the naked eye. But you take an electron microscope and you catch it and you take a picture of it and it freezes it
Yeah.
at one point in space and whatever its path was, but you can't predict its path.
I like this imagery of science freezing freezing events in time in order to analyze them. That's really interesting.
Right. Now, sure, one could argue is that sure, science is going to study things in motion.
Yeah.
Okay. Understandably, if you take a ball, you throw it in the air, you throw it against a wall, you're going to want to measure what its rate of speed was.
Yeah.
And then you throw it again. Is it faster or slower than what you had measured before? But there's a difference between throwing the ball at an infinite rate of speed versus whatever you threw it at. So
Yeah.
science is still looking at slowing it down to study it, because infinitely sped up, it can't fix anything.
Yeah.
Even the speed of light, which is the fastest thing that can travel, is already fixed at 186,000 whatever miles it is per second.
Yeah, that's true.
That's not infinite. There is
Yeah.
a point where it kind of slows down, quote, slows down. Science can measure it, and it has measured it. It's come up with, this is how fast light travels.
Mm-hmm.
Okay. So then, by so doing, science creates a plane of reference or coordination that it requires as science. Okay.
Yeah.
Plotnitzky continues, next paragraph. Philosophy's thought may sometimes hold to a virtual concept by slowing down or freeze framing it. Okay. Let me stress virtual concept. Okay, virtual means that it's not actual.
Yeah.
So philosophy is dealing with the virtual. Science is dealing with the actual. Science attempts to take the virtual and make it into the actual.
Right.
Okay.
That makes sense.
Philosophy can also slow down and freeze frame the virtual concept, sometimes holding it, as they say.
Yeah.
It's not the same thing as science, though. We're dealing with a virtual concept because, think about it. Concepts, no matter how you define it, they don't exist actually.
Yeah.
They exist, but they don't exist. Some might say they exist in the mind, they exist as a brain state, whatever it is. But it's something that's virtual because you can't point to it and say, boom, there's a concept, or boom, there's the thought that engendered the concept. You acknowledge its existence. We have such things that we call thoughts. There is such a thing that we call thinking, but these are all virtual.
Yeah.
Okay. So in the case of thinking, we'll run with this one. I'm not aware that I'm thinking all the time. But if I stop and I say, what am I thinking? I'm slowing it down, freeze framing. What's my thought that I had at this point? I thought of a pink elephant. I thought of the steak that I had last night for dinner. I slowed it down and I freeze framed it.
Mm-hmm.
Okay. So Plotnitzky continues, conversely, science sometimes proceeds with the philosophical infinite speed on, and by creating the plane of immanence in order to create a philosophical concept corresponding to a mathematical or scientific object, or in order to create this object. Philosophy and science appear to need each other, as Deleuze and Guattari say in closing their discussion of the difference between philosophy and science, and what is philosophy. According to them, again a quote from the book, if philosophy has a fundamental need for the science that is contemporary with it, this is because science constantly intersects with the possibility of concepts, and because concepts necessarily involve allusions to science that are neither examples nor applications, nor even reflections. Conversely, are there functions, properly scientific functions, of concepts? This amounts to asking whether science is, as we believe, equally and intensely in need of philosophy. But only scientists can answer that question. Okay.
That's really interesting. Yeah, because especially the point that like basically there are definitely subjects that philosophers discuss that have no relation to science, even though science relies on philosophy in spite of that.
Sure. I still think back to the Heidegger essay that we covered about God is dead, and what Heidegger had to say about philosophy circumscribing, in effect, theology.
Yeah.
Philosophy is what defines the terms. It defines the form of inquiry. It is a science, a body of knowledge in some respects. So, in answer to Deleuze and Guattari's questions, there already has been efforts underway in the philosophy of science. What is science? What is a theory? What does testing look like? What are the presuppositions that scientists might bring into an experiment? Okay. This is all within the purview of philosophy of science. Science needs philosophy because philosophy is what determines the concepts.
Yeah.
Okay. You accept something called gravity, but what's the philosophical basis behind something called gravity?
Yeah.
Yeah. These kind of
Like
questions.
why even ask questions about gravity in the first place?
Right. I mean, human beings were able to exist for centuries without even asking or come up with a concept of what gravity is.
Yeah. Exactly.
So, whole nother subject.
Mm-hmm.
Okay, so going to the next page, page 198. This is in the section Manifolds in Riemann and Deleuze and Guattari. Okay, so we'll skip the paragraph where this is the one essay that we mentioned before on the hypotheses which lie at the basis of geometry from Riemann. Okay, so Plotnitsky says Riemann thus defines manifolds not in terms of ontologically pre-given assemblies, sets of points and relations between them, but in terms of concepts. Let me read this again. Riemann thus defines manifolds, not in terms of ontologically pre-given assemblies, sets of points and relations between them, which is what Euclidean geometry does, but in terms of concepts. Each concept is a particular mode of determination, such as a discrete versus a continuous manifold, whose elements, such as points, are related through this determination. Thus, beyond giving an essential priority to thinking, and specifically to thinking in concepts over calculational or algorithmic approaches, to the point of, in this case, containing only one formula in the whole lecture, Riemann's mathematical thinking is structurally conceptual, which brings it close to philosophical thinking in Deleuze and Guattari's sense. It is based on specifically determined concepts, as against the set theoretical mathematics that followed him, or the mathematics of formulas that preceded him. Okay. Questions so far?
No, that kind of makes sense. Like talking about the concepts and, like you said, the formulas that preceded them.
Right. So the manifold is determined by concepts.
Yeah.
This is what makes it distinct from Euclidean geometry. Euclidean geometry is the ontologically pre-given assembly. Here is a circle. Here is something in the physical world that has a circular shape. Here is a rectangle. Here is something else in the physical world that has a rectangular shape. There is such a thing called a point. There is such a thing called a line, an angle, and so on. These are ontologically pre-given assemblies.
Right.
But the manifold is a concept. You could have, discrete, which is of a certain length, width, breadth, or continuous, stretching out over a long space.
I am a manifold of a dog.
We would use topology to study the doggy.
Yeah.
Yes. All right. So skipping over some more stuff about Riemann, let's go to page 200, toward the bottom of the page. So Plotnitzky says, in contrast to geometry, which has to do with measurement, topology disregards measurement and scale and deals only with the structure of space as space and with the essential shapes of figures. Okay, let me read that again. In contrast to geometry, which has to do with measurement, topology disregards measurement and scale and deals only with the structure of space as space and with the essential shapes of figures. So let's go back to our basketball example. In topology, we don't care about measuring it. Take the ball, let the air out, and squish it. We don't care about it. We care about what's the essential shape of the figure and about the space that it occupies or the space within it. So topology actually is not geometry. It's a branch of mathematics, but it deals with space as itself and the essential shapes of figures.
Right.
Okay. Why? It's because if we're talking about something like a squished basketball, that's going to be very difficult to measure by using a Euclidean geometry, if one cares to measure it.
Right.
Okay. So continuing, insofar as one deforms a given figure continuously, that is, insofar as one does not separate points previously connected, and conversely does not connect points previously separated, the resulting figure is considered the same. Thus, all spheres of whatever size and however deformed, say in appear like shapes, are topologically equivalent. Okay, let me read that again. Thus, all spheres of whatever size and however deformed, say in appear like shapes, are topologically equivalent. So if you take a basketball, completely inflated, and the smooshed up, deflated basketball, topologically they're equivalent. They're the same shape.
Right.
You take a box, smoosh it up, crumple it up, so it really doesn't resemble a box anymore. It's topologically equivalent to that well-formed box.
Right.
Okay.
Yeah, makes sense.
So continuing, topological spaces need not have any metric structure or striation referring to bands, either global or local. Global Euclidean or Cartesian striations, Cartesian here is referring to the Cartesian coordinate system, the xy axis, for example. Striations are not found in Riemannian spaces, apart again from special cases such as those of Euclidean spaces, while local ones are allowed but not required. This is why Deleuze and Guattari say above that Riemannian space, quote, has rhythmic values not found elsewhere, even though they can be translated into a metric space. And hence that, quote, a relation between the two kinds of space necessarily results in Riemannian space.
What are rhythmic values?
Rhythmic values not found elsewhere, even though they can be translated into a metric space. So I would say, so rhythmic is, it's like in music. Okay, what's a rhythm? You can describe what a rhythm is, but you can't measure it. Well, not entirely. You can measure a rhythm, like it's bump, 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 bump. Okay, so you have certain beats there in the rhythm. But I think the point here is that with rhythm, and it's like music. Music doesn't sit still. It's always in motion. Okay, Riemannian space has rhythmic values not found elsewhere. It's not fixed. That's how I read it.
Okay.
Okay. So he continues, when we consider the discussion of space in 1,000 Plateaus, the second volume of Capitalism and Schizophrenia, we can see that smooth or nomadic spaces almost inevitably give rise to local striations, reterritorialization, even as they simultaneously arise from them, deterritorialization. In other words, they again lead to Riemannian spaces as both smooth and locally striated. The nomos of the smooth space, as against the logos of the striated space, is defined by the rhythmic interplay of connectivities between neighborhoods, which defines topological spaces in general rather than Riemannian spaces, defined by local Euclidean striations.
Okay.
Okay.
I like what he said there about deterritorialization and reterritorialization, which we talked about last time.
Right. So in the reference with capitalism, because 1,000 Plateaus is part of Capitalism and Schizophrenia, when you take an object away from where it was, you are deterritorializing it, plopping it somewhere else.
Right.
Reterritorialization is the action of where you're taking it to plop it somewhere else.
Right.
Okay. So what capitalism is doing with lots of different things, most particularly workers, is that a worker who loses his job in a factory town can or must, feels he must, move to another town to take another job. So he's been deterritorialized in his hometown and reterritorialized somewhere else.
Right.
Okay. That's a whole deter and reter because my mouth hurts if I say that too often. Reterritorialization. Too many syllables.
Right.
Okay. So the point about striations is bands. Okay. Like muscle is striated. There are many different bands that are woven together.
Mm-hmm.
Does that make sense?
Yep.
So smooth spaces inevitably give rise to local striations, even as they simultaneously arise from them. In other words, they again lead to Riemannian spaces as both smooth and locally striated. Okay, so the spaces are existing at the same time. You have striation and then you have nomadic striation. Okay, so I guess one way to read that is the nomad is moving from place to place without a fixed point of reference or at a fixed place, but one can do that within striations. So if
Okay.
you're a nomad coming into town, okay, you don't have a fixed hometown. You're coming into a new town. You wander along. You check this out. You check that out. You check this out. You check that out. So you are the nomad moving within a striated fixed spot.
Right.
The two of them can exist simultaneously: the nomadic and the striated.
Right.
Okay.
Yeah.
Okay. So moving to the next page, 202. Manifoldness and materialism, and Riemann and Deleuze and Guattari. Okay, so Plotnitzky continues. This view of space, Riemann's view of spatiality, also allows one to extend Leibniz's ideas concerning the relational nature of all spatiality. The actual space is now no longer seen as a given. Ambient, or flat, Euclidean space, or in Hermann Weil's words, Weil himself was a mathematician, a residential flat. Flat is a fitting pun here, meaning that a flat is an apartment, where phenomenally geometrical figures or physically material things are placed. Instead, it emerges as a continuous manifold, whose structure, such as curvature, would be determined internally, mathematically or materially, for example, by gravity, as in Einstein's general relativity theory, based on Riemannian mathematics, rather than in relation to an ambient space. Ambient meaning that it's filling, like ambient music fills the space, fills one's senses,
Mm-hmm.
Euclidean or not.
Right.
Okay, this is about actual space. It's not Euclidean space; it's Riemannian space as
Right.
the manifold. Okay, so continuing.
Right.
Einstein gave a rigorous physical meaning to these ideas and extended them by arguing that space or time are not given, but arise, are the effects of our instruments, such as rods and clocks, and one might add of our perceptual and conceptual interactions with those instruments. Space is thus possible as a phenomenon, or concept, by virtue of two factors. The first is the presence of matter and technology, such as rods and clocks, or natural objects that function in this role. The second is the role of our perceptual phenomenal machinery, a role that one might argue to be a primary condition of the possibility of space, along with time, which machinery is still due to the materiality of our bodies. Okay. So in other words, what Einstein was getting at is that space and time are not already there. They arise because we have our perceptual mechanisms and we're using instruments to measure space and time.
Yeah. So
Okay.
it's like we define those concepts with our measurements of them, sort of.
Right. Also, like we were saying with gravity, you can't point to something and say that's gravity. Gravity is
Hmm.
something that emerges, it arises from measuring it.
Yeah.
Okay. Now, the general understanding is that what keeps us on the Earth and not floating in space is gravity. Okay. But then there's the gravitational coefficient and all that stuff that you might have remembered from physics, if you ever took a physics class.
Yeah, I did in high school, I think.
Yeah. But you have the formula for measuring gravity, and then you could use the instruments in the lab to measure the coefficient of gravity. Gravity on Earth is not going to be the same as on the Moon, the same as on Jupiter, same as on any other celestial body. Okay, you
Right.
can measure what the difference is in the gravity between that body and what it has on the Earth.
Yeah.
Okay, so moving right along, next page 203. Plotnitzky continues. It would be more accurate and closer to Riemann to say that space may be given phenomenally at most as a three-dimensional manifold, as a kind of free, smooth space with possible striations. Physically, it may be, and in Riemann and Einstein or Leibniz's view, could only be coextensive with matter. Okay? Space is coextensive with matter. What's matter? Something solid. Maybe not something solid necessarily.
Hmm.
Water vapor is matter of a certain kind. But space, given phenomenally, and it's coextensive with matter. So another way to look at this too is that it's really hard to conceive of pure space, in other words. You can define space by reference to something in the physical world.
Yeah.
Okay. So, like I hear on my desk, I have many things on this desk, and I can define the space between these things, between myself and the monitor, between the two speakers that are behind it, between myself and the cup that's on the desk, how close it is to my smartphone, and so on and so forth.
Yeah.
That's how I'm defining space. Okay?
Space is a manifold.
Space is a manifold. That's right. So moving on, Plotnitzky says, Deleuze-Guattari's physical model of the smooth and the striated converts this transformation into a grand conceptual and historical conjunction of physics and political economy, and of both with geometry. Okay, political economy is what economics used to be, where you're not studying, as contemporary economics does, using things like formula and optimization and stuff like that. Political economy is what are the politics involved in creating an ordering of goods and services, purchasing, markets, and so on. So
Okay.
they're using Riemannian space, the mathematical concept, the underpinning of this, to apply it to political economy, capitalism.
Right.
Okay?
Right. Yeah, that's interesting.
Yeah,
It kind of makes sense to apply it to that too.
it does. But this is this is where people really get confused. I mean,
Yeah.
I remember when I was doing the postmodernism series with James last year. He says, yeah, when I was in that course at wherever it was, University of Texas, somewhere in Texas, he said the instructor assigned to us 1,000 plateaus, and I thought to myself, oh Christ, here we go. And he's
Yeah.
like, I couldn't make head or tails of it. Well, no shit.
Yeah. I was confused when I first read that too, because it was the first thing I read by
Which is
Deleuze.
why I never recommend Capitalism and Schizophrenia to anybody that is new to Deleuze.
Yeah, probably.
If anything, I would recommend the book that we've been going through, because this shows some of the basis behind all that. To understand anti-Oedipus, you got to know something about Freud and then Lacan. To understand 1,000 plateaus, as we're getting to, you got to know something about capitalism, Marx, and now Riemannian geometry.
Right. Yeah.
Okay.
There's a
So
lot of
continuing.
extremely complex concepts that go into it.
Yes, sir.
And like based on the history of complex historical thinkers too.
Yes. Okay. So next page 204. Plotnitsky continues. The 19th century brought physics and geometry into a new conjunction. Under equally revolutionary developments of both the politico-economic history of capitalism and of the social and economic sciences, from Adam Smith onward. So in other words, in the 19th century is when you started to have a combination of, okay, so economics is, at least according to the Greek view of it, how to arrange a household.
Right.
But now economics is bringing into, how does one measure space? When you measure space, you can control the space. This is where geometry comes in. Physics. How are we going to produce X, Y, and Z in the factory? What are the new discoveries in physics that would allow us to create something like steel? Chemistry is involved. Other sciences that are involved.
For sure.
Also the sciences on how does one optimize production?
Yeah.
Measuring. Okay, so this is all taking place in the 19th century with the Industrial Revolution.
Yeah.
So then, next page 205, Plotnitsky continues. Roughly at stake here are the complex, heterogeneously interactive and interactively heterogeneous relationships not only between neighborhoods in a Riemannian space, but also between such spaces themselves. Our mathematics and physics on the one hand, and our neuroscience on the other, we're talking about brains here, tell us that to the degree that the processes that define nature and life in our brains, neural networks, can be mapped, they are likely to be mapped in terms of Riemannian spaces and of the interplay of the smooth and the striated within them. The same mapping needs to be deployed when we approach our politics and culture. It is not only a matter of mirroring such Riemannian manifoldness from inanimate nature to life, to bodies, to brains, to thought, to culture, to politics, but also and primarily that of continuous relations that manifoldly connect these manifolds. This is a new kind of, quote, landscape architecture, the architecture of many landscapes, in which these spaces coexist and horizontally interact without necessarily mirroring each other. So, putting it simply, looking at politics and culture in terms of a manifold, there's a whole lot of stuff that's interconnected when you look at them.
Yeah.
So, to approach it from a Euclidean perspective is not helpful,
right?
Because you're going to miss a lot. To rather approach it from a Riemannian perspective of the manifold, you're going to catch more of the interconnectedness, presuppositions, what one thing influences another, and vice versa.
Okay.
Okay.
What is meant by the horizontal relations?
Instead of a vertical relation, where in terms of a hierarchy.
Oh, okay.
Okay. So one field of study is the foundation for another field of study, which in turn is another field of study, and so on. That's the vertical hierarchical approach. Rather, everything's kind of flat, horizontal.
Okay.
One influences the other, this influences this comes back and influences that, and so on.
Right.
Okay, that's the horizontal. Also remember plane of immanence. Plane meaning that it's something that's horizontal. Could be vertical, depending on what it is, but more often than not, it's horizontal.
Right.
Okay. Next page, page 206. Plotnitsky continues. This view suggests a new horizontal space of science itself, or a new space of thought in different ways to think, either within a given discipline, such as mathematics or philosophy, or, but this is now the same, between and among disciplines. We've already more or less covered this. We can think of spaces or landscapes of thought and culture in an interactively heterogeneous way, in terms of distinct and varied, but actually and potentially interactive maps, arranged and related horizontally rather than vertically or hierarchically. Okay, we already covered this. Something I forgot to mention for an excellent example of a manifold is, or how one represents a manifold, is an atlas. Okay. So an atlas, usually in reference to geography. This is the world atlas or continental atlas or whatever it is that you want to use. But what is an atlas except a collection of different maps that are themselves two-dimensional spaces representing something on the manifold itself. If you take the globe, the Earth, as a manifold.
Right.
Okay? That's what an atlas is. Now, there are many other kinds of atlases, particularly in mathematics, where this is the manifold and you're showing one particular space or a collection of spaces within one space within that. It's a snapshot, more or less, of thinking of the one part of the manifold.
Right.
Okay. So, again, Plotnitsky says, we can think of spaces or landscapes of thought and culture in an interactively heterogeneous way, in terms of distinct and varied, but actually and potentially interactive maps, arranged and related horizontally, rather than vertically or hierarchically. Anticipated by Riemann's practice of mathematics through the interactions of different fields, topology, geometry, algebra, analysis, and so forth, this practice defines non-Euclideanism, mathematical and philosophical, such as that of Deleuze.
Okay.
Okay? And like thought in life. On the last page, he says, mathematics proves itself to be more like thought and life, which is more complex than thought. Then thought and life prove to be like mathematics. That is, mathematics understood, as it has been all too often, as an abstraction from the richness, the manifoldness of life. The idea of a manifold of manifolds is a product of thought as a confrontation with chaos and part of a shadow of the future, of things, thoughts, and the people to come. The end. Okay.
Okay.
So the lessons to draw here is that Deleuze used Riemann and the manifold as an underpinning for looking at things that were unfixed, particularly as science wants to look at them, acknowledging that life is highly complex, is a manifold.
Yeah.
There are striations within life, reality you could even say, but nomadic things moving within those striations.
Yeah.
Okay, so all this again is like a theoretical underpinning of, life is complex, life is in flux, life is moving, life is made of many different things. If you try to box them in by certain measurements or explain everything by science, where have we seen this criticism before? You're going to be missing a lot, a whole hell of a lot.
Yeah, for sure.
Yeah. And that's it.
Awesome. Well, that was fascinating as always. Much more, and just like the other episodes we've done about mathematicians, much more interesting than I expected, since I have I'm like allergic to math. So, but
Yeah,
looking at
Matt.
it in a
Yeah,
philosophical way like that is really, really fascinating to me.
yeah. I tend to shy away from philosophy and mathematics too because number one, it's not something that particularly interests me all that much. But
Yeah,
number two is it can get quite intimidating because just like with logic textbooks, you don't know how much the author is going to rely on notation to explain
right.
something. If they rely too much on notation, you don't know anything about the notation, and then you're going to have to go learn that and then do your practice exercises and stuff like that. And you still might not be able to get what it is they're trying to explain.
Yeah,
And that's not to say explaining what a manifold is an easy thing unto itself. Some people just don't get it.
yeah,
Okay, well, again, like with anything else that I've said in this series on Deleuze, is that you have to read it, reread it, and let it sit with you for a while.
yeah, yeah,
Okay, because as I just said about life, sure, what person is not going to say that life is not complex?
yeah, of course.
There are many different ways that you can explain life. There are many different ways that you can explain a concept. Of particular interest is what Deleuze and Guattari have to say about concepts and what is philosophy.
Yeah,
Concepts are not fixed. Concepts are not of one thing. They are themselves kind of like a manifold.
mm-hmm.
They're combined in many different things. Again, like an abstract concept like justice. What does justice look like? You can't point to it. Justice might be an action. Justice is defined by other concepts that are related to a certain idea behind fairness or maybe morality, and certainly morality and ethics are brought into this, punishment, lots of different things.
Yeah, for sure.
And the concept changes.
Mm-hmm. Yeah,
That's it. No other way that you can explain it.
yeah. Life is complex, man.
Life is complex, that's right.
Yeah.
Okay,
All right.
that's all
Well,
I got.
awesome. Well, thanks as always. That was fun and educational as always. And yeah, we're gonna talk again on Wednesday for the next part of postmodern theology with Shane, right?
Right.
Yeah, so that'll be fun. So, thanks to everyone for watching another episode of the Mindgasms podcast. Hope you found this as interesting and educational as I did. And like I always say, thanks to those of you who have subscribed to my channel. Thanks to those of you who like this video and share it and comment on it. And especially to those of you who contribute to me on Patreon. Really appreciate that. And I'll post the link for my Patreon page in the description for this video, like I always do, along with the links to our recent philosophical conversations. And I love you all. Keep being the tiny beam of light that shines through the almost impenetrable darkness in the universe. And most importantly, always remember this: the funk cures all. And think about the plane of immanence and the manifold. And yeah, any last words there, Tim?
Think about the manifold.
Okay.
Manifold
Uh,
rules.
yes. All right. Well, adios until next time, everyone.